So thank you for the introduction, and thank you for the invitation and the chance to present my university and my colleagues' work. And so I'm excited to show you what we're doing. I'm James Pritts. I'm a PhD candidate at Czech Technical University. The logo up there is our research group, the Center for Machine Perception, and we focus mostly on computer vision and machine learning. And we have several of my colleagues are here today, actually, and they've been walking around, so you can talk to them. This work is an aggregation of these guys' work. I, in particular, like Veet asked me to do a little bit about myself, so I will. I initially got into computer vision working at Johnson Space Center in NASA. And then I worked for DARPA, the Defense Advanced Research Programs Agency for the U.S. Department of Defense for 6 years. So I was in industry quite some time before I pursued my graduate degree. And then I came for these two guys, Jiří Matas and Ondra Hum. They're very well-known computer vision guys. In particular, I work with Ondra Hum as my boss, and he's my advisor. And he did a lot with ransack, robust estimation, and image retrieval. You'll see a lot of the state-of-the-art with his name on it. So very impressive work. So it was a privilege to get to work with these guys. The work is, and then the other guys, of course, you'll see they're broken into sections. I'll be talking about image retrieval, I'll be talking about facial landmark detection, and I'll be talking about text detection. And the title of the talk, if I go here, it's, so I'll go through this slide real quickly. The demo is, the idea is that we will show some robust and working systems. These things are fast, they work well, they work on a really unconstrained imagery, and so and I'll show you some demos and videos to show that. What's also cool is that this stuff is state-of-the-art. And when I say state-of-the-art, I'm talking about in published articles and journals. So major conferences like CVPR or IJCV or PAMI, these are rigorously tested against known data sets, and they've demonstrated state-of-the-art performance. So some of these results are a little older, so I've caveated here, but 2014, 2015, and some of it is state-of-the-art. So you'll see a mix of that. And as I said, they have the constraint that at least for the facial landmarks and text, they work in real time. In the wild means basically unconstrained imagery. And this is more of our applied research. So you're seeing stuff from our group that is the most demo-friendly kind of stuff. We also have a more theoretical side to our group as well. And what you'll see here in the second two parts of the talk is that machine learning is integral to our vision applications. So even though we have some vision pipelines, in components of the pipeline, you'll see some machine learning, and I'll talk about that a bit. And yes, we'll have one deep network, so don't worry. So this is the work of Jiří Matas, Ondra Hum, and Filip Radenovic. This is what he calls image retrieval 2.0. Filip is leading this research now. He's a PhD candidate. And why that? Why that name? Well, first off, I'll start with version 1.0. And our group was really pushing the state of the art, and this work is all the way up to, say, about 2010, 2011, before we moved on to this. And this is what I'll present initially. And this is the bag of words approach with many different add-ons to it to get really good image retrieval performance. And what distinguishes these two, 1.0 and 2.0? Well, 1.0, the query, you have some image that you query. You submit the query, and you want you want the visually most similar things to that image. Even that's a little bit ambiguous. What does it mean to be visually most similar? But let's just go with that for a second. And the results that you will get from the query are all visually similar to that particular image. So I can make it a little more precise, and this is how it's measured in papers. It's simple precision and recall. So if we have a notional example here, this is just notional, not a real result, but a simple database with 10 images, and the demo that I'll show you, there's millions or tens of millions of images there. But in a simple database with 10 images, there's 5 images of the San Francisco Bay Bridge. And suppose that we're in row major order here and they're ranked. Well, you want to look at the performance in precision and recall terms. So if we take the first two, we have our recall increases. We're getting 2 out of 5 here. And we have a precision of 1 because everything is relevant. It's this image. We get a false positive here, so our precision recall curve goes down. And then we improve again, we get it again, and so forth. And this gives us an idea of the performance of the system. In this system, of course, we can return all 10 images in the database and rank them, because there's only 10 images. Of course, you wouldn't do that with millions of images. You would choose a top 20 or top 50 and construct such a curve. But this gives you an idea of how well you're performing, and also it corresponds to the visual, the reality of the situation here. So, but the question is, and this is a bit going ahead of it, but do you really want this? This will get into image retrieval 2.0, what they call, my colleagues call. And the idea is that, okay, you can get 1,000 or 10,000 images of the same thing if you get a 10,000, but that's not interesting. Like, I get 10,000 of the same looking viewpoint of the San Francisco Bridge. Maybe a user might want something more diverse, and we'll talk about that in a little bit. But this is the classical definition of image retrieval. So how does a bag of words approach work? Very quickly, we've already been talking a lot about this stuff. We talked about SIFT and so forth and SURF. And, well, the first thing that's done is key point detection. And typically what's gotten are affine covariant features. We use Hessian affine, but you can use others as well. And then they're described. They're described by a SIFT descriptor. So this region is normalized into a patch, and that patch is given a histogram of gradients, et cetera. And so that's their SIFT descriptor. So these guys are turned into patches and described. This is a 128-dimensional descriptor. So that's the first step. This is your query image. You go to some description of the image in this case. You also extract geometry. So these guys are 128-dimensional. These guys are, this is XY is the point in the image, the X. And this B might be, it depends on how descriptive you want to be. So B could be, for example, it could be an affine matrix, which means it's six-dimensional vector, or it could just encode scale or something. So it depends on how much information you want to encode there, but it's much slower dimensional than the SIFT descriptors. Now, we don't stop there. What we do is those SIFT descriptors are encoded into a code book, a visual vocabulary. So this visual vocabulary is built on a huge corpus of data. These are code words that appear often in the image corpus. And these are mapped to a particular code, and I'll show that in the next slide. And these are kept for the image, these geometry descriptors, which we'll use as well. So you see the visual words here. And I think the next slide shows it a little bit better. So here we have some vocabulary. These are the codes in our vocabulary, so SIFT descriptors that were constructed. And then these guys are in the image. They were found in the image, and they map to D. D was the closest SIFT descriptor to those guys found in the image. So we say that there's a term frequency of 2 there. And we build a histogram of the visual words to describe the image. Now our image representation looks like this. So that's the photometry of the image, basically, encoded as a histogram. It's by the term frequency. Now, so how does it work? So we go to this image again. So we have a query image. Okay, now we have our bag of words representation, and we have our geometries, as I discussed before. This is an inverted file. So what does that mean? It means that if in that histogram the visual word appears, we can find all images in the database that have that visual word. So we can now look at anything that might be relevant. And we go through all visual words in such a way, and then we score them against the query image to see how relevant they are. So those that have a similar histogram, now you're comparing histograms in the representation, those are our most relevant images, and they get a score. And the similarity function is important, but there's a multitude of them in the literature. You can look them up. There's tons of different ways of doing the similarity function. Now you get a short list. Those are our good guys, but we still can do better. We can take the geometry information that was gotten from the image, and now that we have things that we know that have these code words in them, we can make sure that the geometry is the same, and we can verify them. It's like a hypothesis test. If the geometry isn't the same, we reject it. So what happens is that the images are matched against each other using a very simple transformation, affine transformation. It's not the true modeling of the image. That would be a fundamental matrix, for example. But we don't need that. We just need some verification that the geometry is close. And this gives us some way to say that really these things are what we're looking for. And so that gives us a new ranking. So this is the re-ranked shortlist after the spatial verification. And then what we do is we take those things that we're now very sure are the same relevant image, and we do what's called query expansion. This is a very critical step because this is what mostly this talk is focused on, this first part of the talk. And this query expansion takes those verified re-ranked images and goes into the query stage again so that we get other things that are close to it. Meaning that if in the original image, I think there's a slide here, so I think this is a better slide of it. If in the original image we have this region of interest that we've queried here, this is the boxes that we queried. We get some results, and we get spatial verification. So these are the things that are now in that spatial verification box, which was here. Okay, we know that those are good, and we can use those images now to submit a new query. And the new query consists of that, and we get additional guys, because there are SIFT descriptors in here that didn't appear in here, but we know they're in there because of the spatial verification. So we take that information, query again, and we get new stuff. So that's the idea of query expansion. So here's a visual representation of that. Here's the original query box. Okay, those are the matched features. Now those are the new features that were found after query expansion. And we can use those features to continue to get images. So that's 1.0 up to this point. Now we go, so that takes you up to 2010, roughly, in state of the art. Now we go for this, which is, what about this? This is not so interesting. We get hundreds of images of the same thing. So can we find new and unseen information? Place location. What is interesting? What are people really looking at from images? Where should I look in the image? So now I'll show you a live demo. This is a server running in Prague, this image retrieval demo. I'll see if I can do this because I don't know how this is going to work on this side. I haven't tried it like this before. So is it going to show there? Yeah, that's what I was afraid of. So it only shows over here because it's in a web browser, it's not PowerPoint. So if possible, I'd like to get this web page up there. Okay. Aha, perfect. Okay, thank you. I'm going to show you image retrieval 1 and then image retrieval 2.0, what the difference is in terms of an actual user doing this. So now I have an interface, and the user is going to just search the Arc de Triomphe. And hold on one second, I need to turn on something. So to turn on query expansion, okay. So now we search the Arc de Triomphe, and sure enough, we get many results. And is that really interesting? If a user did that in Google, who cares? They have 100 images of the same thing. So they might try something else using image retrieval 1.0. They might do this. They search again. And now they might highlight this particular guy here. They're interested in this sculpture, right? And they might search again. Again, not interesting. Now it's really nice. It found the same images using only the features from this bounding box. So that shows you how discriminative the SIFT is, the spatial verification, the query expansion. So the only thing that was used to retrieve all these images are those features that found in that bounding box. But that's still not interesting. So now we go to image retrieval 2.0. Okay, so I do the same thing. I highlight the box, and now I query, but I say zoom in. Now I get all the details of what's in that box. So this is the actual sculpture. We get many different scales. So it's a much more, the user can explore different parts of the image this way. And this is the contribution that I'll talk about now. I'll show you a couple more interesting demos on this, just to illustrate the point. So that's the zoom in feature. Let's do the zoom out. Let's see. So this is Notre Dame, of course. And now we zoom out. So you may think that this is a mistake, but this little frame here is actually Notre Dame. And of course it can't distinguish that because it matches it exactly with this bounding box. This database contains millions of images from everywhere, by the way. It's from Flickr, just all kinds of stuff. Let's choose this one, and we'll zoom out again. Okay, now we're at the city scale, and you see Notre Dame is there. Okay, so let's zoom out again. Okay, now this dude here, his hand is like a little perspective check where Notre Dame is. So let's look at that dude a little closer. The question is now, if we start with him as a retrieval image, this is a bit tricky, but if we start with him as a retrieval image, can we get back to Notre Dame? Because we see this photo, we know he's on the Eiffel Tower, we know he's got something interesting in his hand. So let's go take a look at it. The question is, can we get back there from just the features in that image, not using our previous results? So I will highlight a box here, I guess, about where his hand is. Let's see here. This is going to work. There he is. So there's Notre Dame. Okay. That's interesting what he was pointing at, but I don't know. I want to see more about it, so I'll do it a little bit more. Now we're back here. But now I want to go even further. I want to check out some of the sculptures. So maybe I'll zoom in here. So now you can go from the Eiffel Tower all the way to the rose window on the cathedral using this technology. And this is real time. I mean, we're actually querying the database. It's being sent here, the results. So, all right, so now we're here. And I can actually, since the demo actually worked, I can fast forward through many of these slides. These are some backup slides too. So the idea is clear. This is image retrieval 1.0. This is 2.0. We got the details. And the idea is that this is an easy thing, basically, this query. And what we really want to do is get some different information. So how does it work? The zoom in, we want to talk about how this works. So really, it's the same system, the same slides you've been seeing, but what we do now is just this short list is re-ranked in a different way. And it uses the geometry, the spatial verification step, basically to re-rank, and the scaling is weighted. So you can see here that you have the number of inliers, those that agree with the geometry transformation, but now that's not the priority. The priority is weighted with the zoom factor. So the idea is using the geometry to calculate the zoom factor, and then you can explore the imagery. So. And I had a question about this from Alex yesterday. He asked how the geometry is stored. And it is stored in the inverted file, but it's fairly low dimensional, as I suggested before. So this is the problem-specific ranking. Here we're interested in zoom in. And that's what we showed when we went from the Eiffel Tower. And it's used in the query expansion to get more zoom. So the query expansion gets the input of those zoomed images and issues another query. You can also do zoom out. I showed that as well. So this is just inverted. So the zoom out is the same. Here are some more examples. Like if in the original image you highlight this, you get that. So obviously you can't see anything from that. You can't take this bounding box and get any useful features from this. It requires query expansion. So, but if we do these types of steps, we can get what this looks like. It's this guy. This is the church in Prague, in the Old Town. All right, so I can go through most of this. This is a query expansion showing how additional features are acquired as we zoom in. This is the zoom out iteration that I showed you. So this was the demo that we already saw. I can skip through these. Okay, so now we go into another topic, which is what is interesting here. So what if you got an image and you're like, well, let's crowdsource this. Let's crowdsource this and see what do people find the most interesting. This is the astronomical clock in Prague. So the clock's down here in this tower. And so what you can do is you can say, given that image, you can see what the density of people taking photos is. Like this is really what's most interesting here. This is not as interesting. So you know where to look when you're doing an image. And the question is, this is another interesting question, what are the most interesting details? So what size of detail are you looking at? Are you looking at a detail, do you want interesting details at 1% of the image, at 3% of the image, or at 10% of the image? And given that constraint, it will find the most interesting details at that scale. So maybe you don't care about the little figurines, but you care about maybe more macro stuff. And so you would specify this, and it says, well, people are taking photos mostly of this, for example. And you can see at the lowest detail, they're really looking at the details of the clock. And then this little thing here is like when the clock goes off, these little guys come out and dance, and there's a little song played and so forth. Maybe you've seen it. So they're also taking photos of that. So another interesting question is, if you're using this technology, you can ask, for each pixel in the image, give me the highest resolution in the database of that pixel, containing that pixel. So you can see that you can get very high resolution images of particularly small details by asking that question. So what is this? This slide we've already really been through. I don't think I have to go through this. So this is a bit about how they hierarchically drill down to find detail mining. And what they do is they cluster images. So you can see here the groups, the clusters. And the way they cluster the images using the geometry information, they look at geometric transfer. And if the geometry transfers correctly, in other words, so in this case, the query image is Q. So that's this guy, the original query image. And we want to look at more details of the query image. So this is the original image actually, but suppose we want to hierarchically drill down. So we look at what people are taking pictures of and group them based on the geometry consistency. And so what we do is we say, like, there's an affine transformation that maps here, and then it maps on top of here. So we know that these groups of features at a smaller level are mapping on top of each other. They're verified. So these are grouping well. We know that we're looking at the same area. So we take these grouped images from the geometry and issue a new query. Here we sort of reject because the mapping isn't close enough. So we reject this hierarchy of this group of images, and we don't issue a new query with that because it's not geometrically consistent. And then these new guys, these new queries are used to mine the details. So this is interesting. So you saw zoom in and zoom out. Of course, it's possible to use those same geometry, the geometry to pan left and right and move around the image. Like so, you can sort of go around the image and get a view around the object that you're looking at, even though you never saw the other side of the building. So this can be used. Well, the idea that they had was to use for 3D reconstruction. So instead of having a system where you go and with a camera and look around the building, you just use an image retrieval system with, use Flickr, download a lot of it, use an image retrieval system and get the images you need from that and the features. So you have access to millions of images, as I said, instead of thousands of images that you might take from a camera walking around it. The complexity of this is actually better, the way it's structured, because here you have to do matching against pairs, image pairs. You have to verify, you have to, without going into detail, you have to confirm against the 3D model, et cetera. This is all done through the image retrieval system, this verification. And so it actually is more scalable in this approach. So we talked about zoom in and zoom out. And now we're talking about sideways crawl, and this will allow us to walk around the building. It's a similar concept. So the idea is that you take your initial query is from one particular vantage point, and then you want to explore the building on the other sides. So this is the same architecture again, but now we're panning left and right here with the geometry, and we're ranking those based on the panning. And so the idea is you might take a picture of the Arc de Triomphe, and then you find this image from the first query issued, but then you can extract features from here and issue a new query, and then you get the side. So we've now walked around the building just with features. And here is some reconstruction results. Now I embedded this video, so we'll see if PowerPoint really always. So let's see, that didn't work. I think if I hit this play button here, it'll work, maybe. That didn't work either. There's like a little play button on it, but it doesn't let you press it. I don't understand. Yeah, yes. That I don't know. I'd have to talk to my boss about that. I mean, it's publicly accessible, but hopefully you didn't see the URL when I was doing it. So, but no.
Actually, I googled and tried to access this URL, but it's the same login.
Okay. No, I don't know what I'd have to talk to them because they've kind of gone back and forth on whether to do that or not. So I'm not sure. But if you're interested in that, then certainly contact me and I can give you the information. I can ask them for permission. If it's available, then I can certainly send it to you. That would be it. So this is the video that they put together of the 3D reconstruction using these technologies, the zoom in, zoom out, and sideways crawl. So they're able to zoom in and zoom out to get the details, and then they're able to get the whole building with a sideways crawl, if the video works. So this is an example reconstruction. So the Czech Technical University provided the retrieval side, and then ETH Zurich provided the reconstruction side, and we joined these two technologies to create these reconstructions, just from image retrieval. No videos were taken, just from a database. I think there's more, but I don't think there's a point in showing it, so I think you get the idea. So. Thank you for your help. This is a very famous computer vision image, by the way, this Oxford Bridge. It shows up everywhere. I don't know why, but people are obsessed with it. So. They're like it's like the Lena image that you see all the time.
You could reconstruct Google Maps. Did you try to sell yourself to Google? Maybe they will start from $1 billion.
I never talked to Google, so. Oh, I got it. It's okay. I can do it here. So the message from this talk is never embed YouTube videos in your PowerPoint presentations. So. All right, so this pretty much concludes the image retrieval portion of the talk. We'll move on. I think we've seen this. And this was some work as well. I'm not going to show this video because of all the problems, but they continued with this work, and they constructed images from completely different illumination conditions. So finding day and night features and then merging them by finding the transition between day and night. So they can get completely different features on the image and use them to reconstruct by taking from both day and night. But then you need to find the transition to sort of link them together. And that was actually that paper there, Philip is now in Las Vegas presenting it, or he was a week ago at CVPR. So that was the most recent work. So now I'll move on to a different topic, which is facial landmarks. So this is the work of Vojta France, Jan Čech, and another colleague of mine, Michal Žičarz. His picture's not here, but this is their work on facial landmarks. And so what is a facial landmark? It's very basic. I don't know all the technical names from it because I think each landmark has a face, but it's basically salient features on the face. Like these things at the corners of the eye here, and like the corner of the mouth and so forth. And the idea is that you have this model, you have these interesting features, and you want to track them. And you want to track them since they're viewpoint invariant, and you want to use them for different tasks. Gender, age, identity estimation. You might want to look at head pose, how the head is oriented, or even reconstruct the face. And facial landmarks can be used to do all that, but for these tasks, they need to be very accurate. What is being shown here is the first stage. I'll get into it in a second, but this information is old, of course. The slide was made a few years ago. But what you have is the blue represents the gender estimation, which is male, and pink, female. And then the age was estimated at 34 and 28. I don't know, or what is it, 34 and 28? I don't know how old they really were. I guess they really were 34 and 28, so it got it right at the time. And then this estimates the yaw and pitch, meaning like, is your head turned and is it rolled and so forth. This is the first stage of the detector, and I'll talk about it in a second. Here is the same algorithm applied on a Czech 500 crown note. So you can see that it estimated the orientation of the face. This is just a likeness, of course. And then it put it over. So these are the landmarks projected onto the image.
How old is she?
How old is Kate? Now? Oh, that's a good joke. She's a few hundred years old, I think. I don't think, the algorithm crashed, I don't know, so. I see, yes. By the way, the grivna and the crown are 1-to-1 right now, so this is like 500 grivna. So the input is an image, and it can be, here's some more examples. So who is this guy actually? He's some Czech dude, but this might be, no, Wenceslas, I don't know. I think it's King Wenceslas on Wenceslas Square, but I'm not sure. That's also kind of misty. But the input is an image with arbitrary viewpoint, and the output is facial landmarks. And there's a couple different modes. The most landmarks are 51, and I think these are standard, by the way, sort of standard accepted landmarks of the face. And they output the 6 DOF, degree of freedom head pose estimation. That's what the bounding box represents. And then this method gives you a 3D face reconstruction. It's a sparse reconstruction, and I'll show you how that works. So this is the landmark and pose estimation pipeline that I'm presenting, the method that I'm presenting, and basically all this slide represents is that this whole guy is an initialization stage, and then there's there's a reasoning in 3D, some optimization stage at the end that gets the shape of the face, the pose of the face, reprojects it in the image, and tells you where the landmarks are. So what I'm going to talk about first is just this initialization stage, because this guy is a nonlinear guy, and so you need a really good guess here for it to work robustly. And I'll talk about how this guess is achieved. So the first thing is the face detector, and the face detector is so I suggested before that it provides the estimate of roll and yaw. And it also provides the scale, so you're able to at least normalize the image with this information. So you can back out the roll, and just, if the face is tilted or so forth, you can make it into an axis-aligned bounding box and scale it. The detector is based on wall boost. What is wall boost? I won't go into too many details, but if many of you are probably familiar with boosting, or just boosting classifiers. And the idea is that you take a bunch of weak classifiers, train a linear classifier, and you get a strong classifier from that. The most basic one is AutoBoost, but the Violo-Jones took it such that instead of creating a strong classifier from n weak classifiers, Violo-Jones sequentially tested the weak classifiers, and then after a while ended when they were confident enough. And this sequence was done, they were ranked, but the where to stop was sort of a heuristic. So they thought, well, we test, it's still a face, so we think it's good enough. Wall boost is a principled way to calculate likelihoods and just end the testing of the weak classifiers. That we're really confident this is a face, so let's go forward. And the weak classifiers are very simple. They're like binary patterns or hard classifiers, like edges and so forth. And this idea company is a spin-off of Czech Technical University, founded by Jiří Matas, and this is a commercial detector by them. So what does it give you? It gives you the face detector. You saw it also in the first slide. It gives you a bounding box. It gives you a roll and a yaw. And so from the bounding box and the roll, you can do the image normalization. So you back out the roll, make it axis aligned, and then you scale it to some standard size. And I forget what the exact size is, but it's normalized. And then you get the affine transform for the normalization, and you get the normalized image. Now, what happens then? We have a bounding box with a normalized face that's axis aligned. Now we need to detect the initial guess of the landmarks. So what is used is a deformable parts model, and I'll talk about that in a second. In fact, several deformable parts models are used based on the yaw estimation. So the idea is that if you have your head tilted like this, like you swivel your head on the axis, different landmarks are visible. So based on this yaw, 0, 45, there's only 3 here, a different deformable part model is used. So it selects the visibility just based on the yaw. It's very simple. So that gives us the visibility. And so what is a deformable part model? Well, you can think of it as like, so here's the idea is that, I may have, okay, I see it's here. I'll get to that in a second. So before I go into detail about these bounding boxes, so you have some bounding box where you're taking measurements. So here's one landmark at the center of I think it's here, and that's the bounding box around it. So I'm taking some sort of measurement around that point in this bounding box, and the same here. Here's the nose. You can see this bounding box is much larger, so I'm taking measurements from that whole region. I'll describe what kind of measurements in a second. That's on a future slide, but just go with me for a second on this. And the idea is that we have these deformable part models. And a deformable part model is a prior, basically, an MRF prior, if you know what a marker of random field is. It's an MRF prior on the location of these landmarks. In other words, like we have the measurements, we have the independent measurements from each bounding box. Is that a feature? Is that the feature we're looking for or not? Or is that the landmark we're looking for or not? But of course that's very noisy. I mean, you might get something that's not a landmark that looks a lot like a landmark just because of the image. So we put this prior on where the locations are, and these are like springs. If these guys get too close, like the eyes, if they get too close, then there's a penalty. There's an energy that pushes back. And so you have the response from the measurement from the bounding box as your unary, and you have the pairwise interactions from all the different the features. So if they get too close, then they push back with some energy. And this energy is minimized through inference. And the idea is that the inference, which is nice about this initial solution, is that it's global. For tree structures, you do use dynamic programming, and you get a globally optimal solution. And so you can be confident you're not stuck in some local minimum with your initial guess, at least. If you have good features or not, that's another question, but at least you can be confident you're optimizing it properly. So here are the three models. This is like the full frontal face, this is profile, and this is like half turned. You can see the different visibility here. This is trained, of course. This is a structured SVM problem. Structured output learning is used to train the classifier. There's no details on this. This is a loss function here, but I won't go into it too much. So the idea is that this is the landmarks themselves. You can see that these bounding boxes are the same picture. We have different landmarks. And what's done is that the bounding box defines the area we're taking measurements. Like we want to say, is this guy here a landmark? So what we do is there's a local binary pattern. What a local binary pattern is you have a center pixel, and you test to see if the pixels surrounding it are great. It's very simple, greater intensity or lesser intensity. That's all it is. If it's greater intensity, you put a 1 there. If it's lesser intensity, you put a 0 there. And since you have the center pixel and you have 8 surrounding pixels, you have 256 possible descriptors from that. So you get a 256 dimensional vector, descriptor vector from that. And wherever and this can be encoded that way. So these just show that the different types of features you'll get. So if it's a flat area, then all these will be turned on because they're all more intense than the center pixel. These are all less intense, so it's a uniform region. Here is an edge because these guys are less intense and these guys are more intense, etc. So this is a way to describe the texture in this bounding box. So the local binary pattern is computed at every position in the region of interest. Our region of interest is this bounding box. Okay, and so what you have is they're computed over several scales, so there's some scale invariance. Remember, we've already normalized the face itself. So we don't have to have that many scales in the image pyramid because the face has already been detected and normalized. We do need to search over some scale, though. And then what happens is that since we have 256 possible values for the descriptor, and at these different scales, since we're subtracting the edge effects, this is the dimension of the descriptor. It's quite high dimensional descriptor. So what you do is this region of interest, for example, turns into a 75,000 dimensional vector. Yes?
256 is the value of 8 bits. So it's not 256 bits, no?
Well, what happens is that you need to encode it as a descriptor.
We have some technical problems in this area, so probably if you have some questions, just ask James and then we'll continue. So sorry about that.
Did you try to use landmarks around the pupil to check the gaze direction?
So what was done, as far as I know, and so I'm presenting my colleague's work here, but what was done is age, gender, and expression estimation. I don't think they were trying gaze. Or maybe they did, but it's not presented here. But that's what I know that they were trying.
And what about face recognition? For example, you try with different coloners also. 0 degrees 15 plus minus 15 and plus minus 13.
You mean like to to say that this is a particular person. Like, so I will show a 3D reconstruction example of the face. Like, you can get a very detailed model. But as far as I know, they didn't try biometrics. They didn't try to fingerprint a face and say this is John, this is Jack, this is whoever. So as far as I know, no. This really work was to get the idea was that this work is to get the most accurate landmarks and very fast. And then you can, of course, do all these applications. But really the focus of this talk was how do we get really accurate landmarks in a reasonable amount of time, like real time or super real time, for example. And what you do is you take those and you would use those as input to something else those are applications you were talking about, for example.
Mm-hmm.
How do you deal in 3D construction with different lighting conditions and similar factors?
Yes, that's the next slides. What happens is that you have, the fact is that you have a very constrained environment. The faces, we all have about the same face, plus or minus some PCA vectors, basically. So the idea is that during the reconstruction, you have a very regularized optimization. You have a mean face model, and you're adding components to those mean face to stretch it and to deform it and so forth to what's in the image. And the idea is that you have a very good initialization from these stages I was describing before, and now you take this regularized optimization, this nonlinear optimization, and because you have this regularization, you're not going to go too far from what a real face looks like. So it really forces us into that local minimum, and that's the idea. And it's kind of clever because you might in the 3D projection, the 3D model, you don't have these pairwise interactions like you do in the deformable parts model. But what is a substitute for that is this regularization, that these features can't move too far from the mean model. So you still have that in there in a different way.
What do you use?
Okay, just a second. The projector burned. I mean, it's not a. So James, what up to you? So you can continue. You can finish without projection, or we can move to the screen here, and you can continue with the 3D.
I think the screen would help.
Yeah. Okay.
I can continue to answer questions.
Yeah. So you can continue.
But if we're running too long, we can cut it off too. Just let me know. So.
No, it's fine. So you can continue answering the questions, and we'll install.
About first part, what was the factors of models?
Yes.
How many descriptions do we have for each box?
For each bounding box, you mean? Well, of course, it depends on the image size, which they normalize a bit. But for a whole image, you might get 1,000 descriptors. And these descriptors are reduced drastically when they're mapped to the visual vocabulary. So what happens is that you may have that high dimension, so 1,000 descriptors times 128. So you have 128,000, like it's huge, right? But then you map to the visual words, now you have a histogram, which is the size of the vocabulary. And you're probably gonna ask me what the size of the vocabulary is next. And I don't know, I can't give you, it's been a while since I've looked at it, but it's at least in the hundreds of thousands, maybe even higher, so. Or tens of thousands, I should say, so.
About this question, what algorithm you use for search in such a big database?
Well, it's the inverted file. So there was this posting index. So the idea is that you can get very quickly through this reverse lookup all relevant images. So all you have to know is that a visual word appears in the query image, and then you have it stored all images that contain that visual word. So it's just a lookup. It's a very simple lookup to get those images that are relevant.
It's by the geometry, yes?
No. In the first stage, you just need the relevant images, something that could be relevant. So you need to find out those images that have a possibility of relating to your query image. And so you use an inverted file to do that. And all that means is that you have your histogram, which describes your current query image, and you look at where the non-zero entries are. You look up that non-zero entry, and it's going to be indexed in some database. You go to that index, and that index points you to all the images containing that visual word, and then you pull all those.
How do you find these words?
The words are stored. That's a database that's been... So what happens is that when you create an image retrieval database, you take millions of images, right? And then you extract the SIFT descriptors from them, and then you create the visual vocabulary, and that's done with k-means. So you use k-means to construct the visual vocabulary. the centroids of there's many ways to construct a vocabulary. I'm giving you the simplest way. So this is a very simple way to do it. But so now you have the centroid of your Voronoi cell, which is going to be your visual word. And now you have the vocabulary. Those are your visual words. And you know where those came from. I mean, obviously, since you use the images to generate the descriptors which generated the visual words, you can map the visual word back to the image. And so you know where those visual words came from. So anytime you get a visual word, you know what image it came from. And then when you do your new query, when a new image comes through, and you describe it with descriptors, you extract descriptors, those map to visual words, and then it's just matching them. It's really simple.
So you do this visual word by all descriptors in image, yes?
Well, the visual words are all descriptors in all images in the database. So you have a huge database of millions. It's a lot of processing power to create this. So you have a huge database in the millions, you extract all descriptors from all images, and then you create your visual vocabulary, and you use k-means on these 128 dimensional vectors. And you calculate these centroids, and those are your visual words.
Some clusters.
Clustering, exactly. Yeah, it's something like a clustering. But you have to have a representative for that cluster. You have the cluster, but you need some vector that represents the mean value of that cluster. And that's what the visual word is.
So when you search
Сейчас,
image, you
Там
take
тем не будет видно.
all images
Там
from
проблема.
cluster in which belong this image.
Oh, it's the other way around. So you just start with your query image, okay? No cluster. You start with your query image. Okay, you get the descriptors, the SIFT descriptors, okay? And then you find out what visual word it maps to. That's easy, k nearest neighbor, or one nearest neighbor. What's its nearest neighbor? Then distance. So you find out the nearest neighbor, now you know what visual word it belongs to just by distance matching through nearest neighbor. And then you look up all images that contain that visual word from how you built the database.
So, James, because we in Ukraine, we have solution for all cases in our lives. So we have additional electricity, etc. So you can use continue with this big screen.
Okay, thank you. Okay, where are we? So this is, I was talking about these, so there was a question, you had this, and that's where we ended. Okay, so that's cleared up. So we have this very high dimensional guy. It looks scary. I was surprised too. This doesn't work anymore. Okay, of course. We have a lot of training data though. So we need a lot of training data, and the idea is that this is also a structured output learning problem. And you have this description of the measurement region. And what I'm showing, I keep doing this. Might as well. It's a habit. So what you have here is you have the blue guy is this particular landmark, okay? And so you're looking at the response of this blue guy, and you can see that, of course, it also has a response on the right eye as well because of the symmetry. So that's interesting, because I'll talk about this in a second. Here you have the nose, the green guy. You see the responses here. This is the training classifier. The training is interesting because what's done is you have this huge vector, and what you want to do is learn a weight. And you want to find out which elements of that vector are most discriminative, basically. What is telling you the information? Because you have an annotated data set, you have supervised learning, you know what's right. Someone went through and actually manually marked all those landmarks, poor PhD student or master student. And then you do the supervised learning and you learn the weights which tell you which are the most discriminative features. So now you have basically learned a feature descriptor because you can weight your response from the LBP pattern and find out which of those locations in my region of interest are really telling me this thing is what I want. And the learning, there's a loss function that's minimized this is discriminative learning. And the loss function, of course, you have the symmetry problem, but what's done is that you know the annotated point, which is your x, and you know your estimated point, which is x prime. So since you know the annotation, it doesn't let your loss increases as you get too far away from the ground truth point. So you won't make the mistake, at least in training, of confusing the left eye with the right eye because you're penalizing with a distance, Euclidean distance in the image. Okay, so that takes us to the 2D part. I have this, also this, Okay, I have a video here, which I'll try to get going. I think I can do this one, maybe. If we could just get to the directory that this presentation is in. So wherever this is, we can launch the video. This is just the initial guess. So I wanted to show you the deformable parts model without the refinement. So this is what's being put into the nonlinear routine. And the idea is that maybe it'll work. Oh, it's working here. Great. Okay, perfect. We didn't even need to do that. So this is some video on the news, and you can see the different. So this is switching between these two guys. This is the profile, the 75-degree view, I think. This is the frontal view. And you can see the landmarks are estimated. You see they're very noisy, though. Like this is all from 2D. So you can see the bounding box gotten by the face detector and the DPM overlaid on top of it, and so forth. So that's good enough, I think. So now we go into the 3D part. Let's see here. I can do this. Okay, so now we're here. And now we're going to the pose solver. So what happens is you have your 2D estimations done in normalized space. We back out the normalization. Now we're back in the original image space. Because we have the normalization over here, now we back it out. So now we have a DPM in the original image. And what we have is, we have the 51 landmarks. And we have a sparse model of the face, gotten from thousands of training images, or even. But it's a 51 element, it's a 51 point sparse model of the face. And what's gotten is we calculate the mean face, the mean position of those landmarks in 3D. And what happens is that we have, they're labeled, right? Because the 3D landmarks correspond to the 2D landmarks. So like the corner of the mouth, we know where that is in 3D. In the mean model, we know where it is in 2D from the DPM. So we can do a PNP problem to get the 3D, initial guess for the 3D pose of the reconstruction. PNP is a classic computer vision problem. And so there's this guy that's minimized, which is, this is projection. This is, the XI is the mean model, that's the mean face. It's projected into the image, and the distance is subtracted from the 2D landmarks in the image. So reprojection error is minimized. And it's robust, so they do it with ransack, and they follow up with maximum likelihood estimation. Okay, we did that. Now the fun begins with this guy. So this is the final refinement, and this is what gives the nice result, which I'll show you in a second. What does this nasty equation mean? It's not really that nasty, actually. Well, first off, you have the mean face. What is this x sub nu, or x of nu? X naught is the mean face, so we have all your faces are averaged together, and then we do principal component analysis. So those most dominant components, you can add some scalar to, and you can deform the face and change the shape of the face. So the idea is that you have a mean face, and now in your estimation, you're adding some differential to that face to make it fit your face. And this is what provides the regularization, because this n, this nu, is the scalars that what you're dotting the principal components with. So you regularize it by not letting them get too large. You penalize, if you really want to stretch the face out large, you're going to have to pay a penalty in this 2 norm squared. This is just the reprojection of the mean of the face, the current estimate face. So of course, now you don't have the mean face because you have it as a function of this nu. So this is the actual face that you have estimated. This is just a projection matrix, counter calibration, rotation, translation. You reproject it into the image, that's what this means, the sub E. And then you look at this, you have that point in the image, and you look at your classifier response that we talked about before, and see how good the classifier response is for that reprojected point. And if the classifier response is really good, then you have a good estimation of the point. And then you multiply it by the visibility, which is a binary variable. The visibility, like if it's occluded, of course, it's going to be 0. And that's gotten simply from, remember we talked about the 0, for these 3 choices you have for the DPMs. So this VI is set a priori before you go to this nonlinear estimation for this particular frame. It's estimated directly from the DPM you've chosen. And so the shape and pose are jointly estimated, the visibility is fixed, and the landmarks are gotten from the reprojection of 3D into the 2D. So I'm gonna, before I show you the final results, I'll just summarize this whole framework. There was a 2D model with MRF prior given that gives you a globally optimal initial guess. We have, from the result, we have a sparse 3D face pose and reconstruction. So sparse reconstruction and face pose estimation. The simple handling of landmark visibility. You just have 3 choices, depending on the DPM you choose. It's real time, and as of, this is a little bit of older results, so as of 2014, it was state of the art. So here's the final result, and let's see this guy go. Okay. So these are 51 landmarks being tracked in pose estimation, and you can see the eyelids going and the fade and the lips moving and so forth. Okay, I think it's enough of that. There's another one, I guess. Oh, let me show this here. I guess it's interesting too because he has glasses on, and it's a child instead of an adult. And there's some occlusion. Let's see what happens with occlusion. So he's trying to mess it up a bit. So what are some other applications? You can do 3D face reconstruction. Since you have the sparse data points, you can create a mesh, or you can fit a mesh to those sparse points, refine the mesh, and do a texture map and do 3D face reconstruction. And you get this dense reconstruction out. And in fact, like, these are deceptive because they didn't even bother optimizing the mesh. They just fit some mean mesh to the 3D landmark estimation and then texture mapped it. So they didn't even bother to optimize. It's just an average mesh of the face. So it wasn't really even that clever. It's still kind of very visually pleasing results. Here's some examples from standard data set. So this is like a benchmark data set. So the summary, we've already gone through this. The performance is super real time, greater than 50 frames a second, and it was fairly competitive in benchmarks. So should I keep going, or is it too much?
Yeah, 10 minutes.
Okay.
Like 10.
So now we talk about text detection. This work is very well known. Lucas Neumann is now on a Google Fellowship because of this work, and he's published at many conferences and got many awards for this work. It's evolved over some time. So how do we define text? Text is defined as anything that can be represented as a Unicode string. Foreign language, whatever, it doesn't matter. If it can be done by Unicode string, we consider it text. Seeing text in the wild simply means that there's snippets of text. They can be different scripts, different fonts, different viewpoints, different lighting, different materials, etc. And these images, and I looked at the benchmark data set, by the way. This is considered an open problem, even for the deep learning techniques, because on the benchmarks are extremely difficult, and the results are still leave a lot to be desired. So this is a very active area of research. The images are actually, these are not representative of the toughness of the images in some of the benchmarks. So this is a region-based method, and the idea is this: is that the text is there's tentative candidates for text that is nominated. The text is then segmented, and a classifier calls it as a character, as multi-character, as background. So there's a classifier involved that takes those segmentations and says, do we have a part of the character? Do we have all of the character or multiple characters, for example? Or nothing. It can be just background noise. It can be clutter. This is the pipeline, and it's a little bit inaccurate. I'll describe in a second because this has been replaced by something else. And this is the idea is that you have some candidate segmentation. You have the classifier, which has to say whether this is part of a character or multiple characters, etc. So it can group them. And then you find out your text line hypothesis. So Huff transform was mentioned once already. It will be used here again. So now you have some text fragment. You want to know what its baseline is, basically, and that's what this does. This is no longer used really, but I might talk about it because this has been replaced with deep learning, and it works so well that you don't need to refine the segmentation. In fact, they say it sometimes even hurts. That used to be a graph cut in there. So I was going to show a live demo, but there's some issues with it because the resolution is terrible on my phone. So I'll just talk about it. This is a very simple key point detector. It's a local binary pattern as well. And the idea is that this is a hand-designed detector. And the idea is let's look at where the stroke ends and where the stroke bends. So the red is where the stroke ends, so like an end of a particular stroke, and the blue is where it bends. And that's what they're trying to detect, because what they'll do is when they get those key points of candidate stroke ends and stroke bends, they do a flood fill, very simple, to get the connected component. So this is very fast, very straightforward. It works on the Android phone, it's real time. And these are the binary patterns that demonstrate it. So you can see that what it looks like if it's a stroke beginning and a stroke bend. And you get the same idea is that you're comparing intensities to detect these. And here's an example of a stroke end and a stroke bend. And then they're zoomed in. Those two are zoomed in. There's a classification stage which uses SVM. This is a very simple SVM. Like before we were talking about struct SVM, this is simple SVM, just no structure whatsoever. So components are typically assumed to be a character, and what happens is that the SVM is trained with these features. Okay, let me go through this first. So what they do is, in typical systems before this, they assume that each component was a character, but they relax this assumption. And if you get a component, of course, because you're looking at multiple languages and so forth, it can be part of a character, a group of characters, or even a word. And so what they want to do is classify which this component is, or of course background, that's not in here, but they also classify this as junk, and they throw it away. And what features do they use? They have a feature vector in the SVM. The features that they use are simple, except for this one, which is more interesting, I think. But they use aspect ratio, compactness, number of holes, horizontal crossings, and then this is something they came up with, which is called stroke support pixels. And the stroke being that if you took a pen and you wrote something. And this is a very simple method. They do one versus all when they do inference. Because you have these different classes, and SVM is binary, so they do a one versus all test. So these are the stroke support pixels, and they happen to be the most discriminative feature in the SVM, so I'll talk a little bit about them. And you can see some classification results of multi-character, single character, and non-character regions. The stroke support pixel is this. Basically, the idea is that you do a distance transform, and you detect where the distance in the stroke is where the distance is maximized. So, for example, these red pixels show local maximum with non-maximal suppression, where the distance to the edge of the stroke is. And the idea is that the stroke length times the stroke width should be the area, if this is really a character. And that's what this represents over here. And you can see that for things that are characters, indeed, this ratio is true. So if you take the area of the stroke length times the estimated stroke width gotten by this distance transform, and divided by the total area of that actual connected component, if it's a perfect character, it would be 1, a perfect stroke. And you can see here that the ratio is quite high for characters, and then for this blob, it's quite low. So this is used in the SVM to do classification. It's very fast, and it's effective. This is very simple. So once you have the connected components of characters and you verify that they actually are characters, Huff transform is done. So you have these connected components, you have their centroids, you just, in the Huff space, you're estimating radius and theta, your line position and orientation, or your line, the radius and theta defines the line basically in this parameterization. So you just sample these guys that are neighbors. You take the neighbors, the closest neighbor of each one is a pair. It defines the line itself, and then you throw them into a Huff space and cluster. And this gives you the line estimations for the text fragments. And then in the end, you plug this guy into a convolutional neural network. This is one way to do it. This is not the work of us, by the way. This is from Oxford. So that last step has been replaced by this component. And this is a per character convolutional neural network. So given one component, or given the estimation of a particular component, what its extent is, it will maximize the posterior probability of what character it is, given the measurement. And this is done through a CNN. And that's the output of the system that gives you the character string. But it's done character-wise, so this is not a joint probability. It's just maximize the probability of each character. There is work that does do the string holistically, but it's much more computationally intensive. And you could, some people may say, why not use a CNN for the whole thing? Like, why are you going through all this work? And it's because this is very slow. Like, they can maintain real time with 1,000 components. So if you give it 1,000 components to test, it can maintain real time. But if you do the whole image, it doesn't have a chance. So, that's it. So. Are there any questions?
Yeah, we have 10 minutes for questions. Probably more.
if you're ready. Yeah, so, yeah.
I have a question about the first part. You mentioned that there were two vocabularies, one for geometry and one for features, right, for detectors. Well, my question is, how do you build this vocabularies? How big are they?
Yeah, so that's a good question. So it depends on the corpus of their images, and strictly speaking, when I speak about vocabulary, strictly defined, I'm speaking only in the SIFT descriptors. You're talking about centroids, and you're at least in the hundreds of thousands, and possibly even higher. You'll have to look at the image retrieval papers. They define, in fact, that's part of the benchmark. How big is your vocabulary, your code book? And what performance can you get with that particular code book? And there's standard levels, like we use this many, we use this many. So of course you can increase as much as you want, but then you pay a price in sort of storage and performance and so forth. But to answer your question, it's at least in the hundreds of thousands of code book, and probably larger for larger image corpuses. So it's quite large. So.
Okay, I have two questions. The first one for the first part with the image and video, and second for the text one. So for image and video, what kind of database you use to store that and then query? Is it a SQL database or is?
It's a combination. So there is a combination of flat file, SQL, and Cassandra. Because when you're actually learning the visual words, you're dealing with so many images and descriptors, and you have to parallelize it. So we need hundreds of CPUs to do it. And when you're writing and reading that much data, you have to have a distributed database. So the SIFT descriptors are stored in Cassandra, which is a giant source of many of our problems because it's very difficult to maintain. The inverted file, a long time ago, was just a flat file. They were dealing with it manually, but it may be in SQL now. I don't know. But basically, all three are used. So.
And for the second part, did you use your text recognition engine for the capture analysis now?
For the what?
Capture images.
No, I don't know. Maybe they have, but I haven't tried. I don't know what it would output, because something warped, maybe, you know.
A short question about the facial recognition. So you estimate the yaw and roll angles, and where is the pitch?
You mean like this, and you're talking about this and this, basically. That would be, I presume. So
because of the proportions, maybe, yes.
Yeah. So I understand what you're saying. So that was the first stage of the detector, like where that was estimated, right? Okay. For a normalization. So you want it axis aligned and normalized. And I can't answer this because I didn't engineer it, but I would assume that for selecting the correct DPM for the initial guess for the 3D, that the pitch wasn't as critical as the roll and yaw. So that would be my guess, but I can't answer it exactly. So.
I have a general question about LBPs.
Yes.
Did you ever encounter the problem that when you try to classify an inverse image, that it doesn't work because the features are different?
You mean like negating the entire image?
Yeah.
Yeah, that would screw everything up, I imagine, because you're training on your struct SVM is being trained on the original image. So if you inverted it, I don't think it's inversion invariant. No.
So how did you solve the problem of, for example, a text which is lighter than the background itself?
Okay, well, so you're talking, I thought you were talking about the faces. So for the local binary pattern for the text that they designed, that was designed by hand, and there was no learning on that. And I'm sure they have the inverse case in that case. Like, I'm sure they basically designed the pattern such that it's both ways. So that's a different topic. But yeah, I think that they took care of that. So.
Thank you.
Little question, will skin color will be a problem for this algorithm sets for face recognition?
Yes, of course. So I don't know what color space that they were trained in and so forth. Yeah, of course. But I'm sure that was addressed. I can't exactly answer your question exactly, but the training, for one thing, they have the training data, and I'm sure it included skin colors of all type. And so I presume that the LBPs, these features were deemed discriminative even when it was inverted. So, like, go ahead.
What I talk about is because when we do PCA, principal components, I think it will be different for different devices. It will be different. No size, big size, error size, not only.
I see. You're talking about the 3D model, for example. Well, that's okay. So like I said, I didn't do this fine detailed engineering, as I said, but I think that the mean model is close enough because you have a guess. Like I said, the DPM gives you a guess of the 2D features, and you have some correspondence. So it will put you in a rough pose and scale or orientation, relative orientation. And then you do the projection and you do the refinement of these things. I think that because you are dealing with such a constrained model, which is the face, I mean, you can't do, it's not like an unconstrained problem like reconstruction. In reconstruction, we track features and we can reconstruct everything. Here we have a very constrained model of the face. And you're correct that, of course, there's huge variances when we look at people. But because it's such a specific thing that we're close enough into the local minimum where it just goes right down there. And that's my guess, at least. I don't know. So, yeah.
I'd like to have a question about face landmark detection.
About face landmark, okay.
Yeah. As I understand, you model the visibility of key points by choosing proper DPM model.
That's correct. It's chosen at that stage.
And my question concerns occlusion problem. Suppose you have front-looking face, and you cover, let's say, and you choose a corresponding DPM model. And then you covered, let's say, left side of your face with some object.
Yes.
And in this, on this condition,
yes,
would be your algorithm capable to return correct position of visible?
Yeah, that's actually an excellent question because I should have said that during the presentation, I didn't. The DPM is only used on the first frame. And then subsequent frames are used for tracking. So once you establish the initial frame using the DPM, so I hope, like, okay, maybe you would get messed up if on the initial frame he had his hand like this. But suppose it was in a normal situation. Once you have the initial DPM, you get your first 3D model. And now you know at frame 1 what the 3D orientation, pose, and shape is of the face. Then at frame 2, we just use frame 1 as an initial guess. So you don't need to redetect using DPM. There's no, and you're asking maybe like he turns his head and you have a visibility problem, like maybe those points are no longer visible. Typically, it probably wasn't covered here, but I know the people who are doing it that they have some robust solution so that outliers are just are sort of thrown away. So you can look at reprojection error, and if it gets too high, you can just cap it, basically. So it's a robust technique. So for those, if you have an initial pose and some of your points go invisible because of inclusion, those will be outliers, and likely they will either match to a point that's self-occluding, or they will be rejected because their error is too high, and it'll just say that this is not visible anymore.
Thank you. And another short question concerns the structural SVM solver.
Yes.
Do you use your own implementation or some?
Yeah, so CMP, in fact, I think that, well, I don't know if there were some people involved here that wrote it, but we have our own solutions for that. They have a regularized risk minimization for discriminative learning. And so there's a whole, like, this is one way to do it. So they have a whole set of solvers that can do this, and they're quite, I use it myself in my work, and it's quite robust and it's cool. So, yeah. I mean, the structural SVM problem, by the way, is a general form of regularized risk minimization, this objective function when you're minimizing the loss. So, yeah.
We have more questions? Okay, thanks. James, thank you very much for coming here. So here's our last speaker. What is our goal? So we have a panel. I need I think 5 chairs. So the question for this, it will be like 5 people who will talk here. It's a very short question to all of them. If you, for example, living in Ukraine or